So it's looking quite good. So I'm already going to introduce the session. So hello, everybody. Thank you for joining. So my name is Jeronimo Castrillon. I'm a professor at TU Dresden in Germany. So it's my pleasure to welcome all of you to the last session of the conference. And yeah, so the conference, I guess the conference left the best part for last. So this session is about tuning and optimization. So it has a very varied set of topics. We're going to talk about approximate computing, auto-tuning, memory consistency, GPU schedulers, encryptions to mitigate side channel attacks in branch prediction, and also on static analysis to detect errors in instance computation. So as you can see, it's a lot of different topics. So let's get this session started. So the first presentation is going to be presented by Gokul Ravi. So the video is from Gokul Ravi. So all the presenters are here for the Q&A. So Gokul is a 2020 Computing Innovation Fellow. He's pursuing a quantum computing postdoc at the University of Chicago. His research targets architecting classical control for near-term quantum systems. Is mentored by Fred Chong. He completed his PhD in computer architecture from the University of Wisconsin-Madison in August 2020, so very recent, and was advised by Mikko Lipasti. So Gokul Ravi, the channel is yours.
Hello everyone. I will be presenting SHASTA, Synergic Hardware Software Architecture for Spatio-Temporal Approximation. My name is Gokul Ravi and this work was pursued when I was a grad student at UW-Madison. I was advised by Professor Mikko Lipasti and this work was pursued in collaboration with Professor Joshua San Miguel. A summary of SHASTA before diving into the details. So approximate computing is a growing field and designs for approximate computing span the software and hardware space. In more developed solutions, a tuning mechanism is used to determine the appropriate amount of approximation across variables or for each variable. There is a lot of scope for improvement in both hardware and tuning mechanisms, especially when targeting fine-grained approximation. First, the hardware solutions are not flexible enough to maximize execution efficiency in a fine-grained manner. Second, the software tuning mechanisms are less efficient when supporting fluid precision and are generally hardware agnostic. Third, when multiple forms of approximation are employed, there is a lack of coordination between them. SHASTA optimizes across the system stack for efficient approximation. In hardware, SHASTA proposes fine-grained methods of approximation for both compute and memory. For approximate tuning, SHASTA efficiently tunes the approximate variables in an application via hardware cognizant gradient descent. And finally, the end-to-end system is built so that multiple forms of approximation are able to work in synergy, thereby maximizing the execution efficiency. So first we look at compute approximation. So let's start with a single cycle functional unit in a synchronous processor. So usually an architect assumes that all computations on this functional unit will need one clock cycle to complete, and this is irrespective of the computations being required to be accurate or approximate. The reality is that if our application would allow for some computations to be approximate, then the time for such a computation can be reduced so as to match the accuracy requirement and resulting in a new form of clock cycle slack. And this form of approximation is fine-grained and can vary from one operation to the next. So based on the modeling of circuit timing, this graph shows how approximation slack varies with accuracy loss for different operations. So here the y-axis shows decreasing accuracy while x-axis shows increasing approximation slack, and this is averaged over a million random operations. So it is easily observable here that as the fraction of clock cycle, which is the identified as approximation slack, increases, the accuracy worsens. That more important to note here is that this increase in accuracy loss is deterministic, gradual, and unique for different operations. So depending on what is the accuracy loss that can be tolerated, different operations would allow for different amounts of slack and thus can be completed faster. For example, the add, which is shown in orange, allows for 40% slack at 20% accuracy loss, which means it can be almost twice as fast. So for SHASTA, to perform compute approximation, we use this idea of slack recycling, which has been proposed in prior work RedSock from our group, except that here the slack includes the approximation slack characteristics as well. And the idea is that the more the approximation for a computation, the higher is the computation slack and thus greater the benefits. Thus, there is potential for fine-grained per operation approximation via this new form of timing approximation, and this is implemented via slack recycling. So to accompany this fine-grained compute approximation, we design fine-grained memory approximation as well. So we extend prior work on load value approximation, which approximated L1 decache misses, and we extend this in two ways. So first, we bring the load approximation prior to the L1 cache. So if an approximate load is looked up in this pre-L1 approximator, the approximator would return an approximate result which is built from prior cache accesses to similar address. Second, we bring fine-grained control to this load approximation by allowing unique control for each approximate load based on two features. The first feature is what is called approximate confidence, which decides how often an approximate load is looked up in the approximation table as opposed to going to the cache. And this is shown in red in the left figure. The second is the approximation degree, which decides how often the data is updated in the approximator, and this is shown in green in the left figure. So in prior work, all approximate loads used a uniformly fixed confidence as well as degree, which was set statically, but SHASTA allows fine-grained control for each load. Thus, SHASTA is able to enable fine-grained per operation approximation in both compute and memory. So next we look at tuning for approximation. So consider the code example for approximation shown here, which targets 90% accuracy as specified by the programmer. So the operations suited to approximation in this code are annotated by the programmer and they are shown in green. So looking at the corresponding assembly instructions, there are multiple instructions suited to SHASTA style approximation, the load, the add, and the multiply here. Now SHASTA's hardware enables fine-grained per operation approximation. This means that there can be tens to hundreds of approximate operations similar to these three, and each of them can take one out of many approximation levels. Thus, there will be multiple combinations of approximation levels possible for an application, each of which is what we call an approximation configuration, and these are all represented by like the nodes shown in the figure here. So out of these, some of these nodes would meet the 90% application accuracy requirement, and in this figure they correspond to the nodes along the red line. Now a tuning mechanism which is unaware of the impact of approximation on the actual hardware execution efficiency might choose any one of these configurations along the red line as optimal. On the other hand, if you have a hardware cognizant tuning mechanism, it would choose that configuration among these which would maximize the execution efficiency metric of interest. For example, this figure shows different configurations in green for different metrics like IPC energy and energy delay product. So to cater to this, SHASTA proposes hardware cognizant tuning. So further, since this is a high dimensional optimization problem, SHASTA builds its tuning mechanism as a gradient descent based algorithm. The tuning of the approximation configuration is performed at runtime on the actual hardware on characteristic input samples. And as the tuning progresses, for each configuration, the actual application error as well as the hardware execution metric of interest are measured and are used to decide the next step in the tuning process. The gradient descent algorithm moves this approximation configuration along the steepest gradient of efficiency versus error. That is, it moves the configuration so as to maximize the improvement in hardware efficiency gain for the lowest increase in error until it reaches the optimal configuration. Thus, SHASTA proposes hardware cognizant tuning by a gradient descent and achieves optimum metric specific fine-grained approximation. So the combination of multiple approximation forms, which is the compute and memory approximation, as well as a tuning mechanism which controls them in a coordinated manner, can improve SHASTA's benefits in multiple ways. First, it creates a larger tuning space, which increases potential for optimal error efficiency trade-off. Second, there is potential for constructive interference. If compute error occurs on an already errored load, then they have relatively less impact on the overall application error, but a combined efficiency benefit. And third, which is specific to these forms of approximation, the skipping of memory accesses lengthens the transparent chains over which slack recycling is performed. And thus, SHASTA allows for coordinated benefits, which is greater than the sum of individual parts. So now we look at some evaluation results on some approximate workloads from different benchmark suites. So the figure shows benefits from SHASTA at different error tolerance levels. We sweep from 99%, 95%, and 90% accuracy. Now in this figure, the P bars show performance speedup and the E bars show energy savings. So even at 99% accuracy, there is considerable benefit in both performance and energy savings, 10 to 15% on average. This shows that many operations can be aggressively approximated for only a small application error impact. Further, in almost all of these applications, there is a clear monotonous relation between tolerated error and the benefits from approximation. There is at least a 10% improvement in speed up and energy reduction when we go from 99% accuracy to 90% accuracy. Thus, SHASTA is able to achieve considerable benefits even at low error tolerance, and the benefit increases as tolerance grows. And though I didn't discuss in detail here, the paper discusses the fact that roughly half the benefits of SHASTA comes from its fine-grained hardware, 30% comes from the tuning mechanism, and 15% from the synergy between different forms. So the overall takeaways. So error-tolerant applications have the potential for fine-grained approximation. SHASTA proposes two forms of approximation for compute and memory, and also a tuning mechanism based on gradient descent. The benefits of SHASTA are its instruction granularity control, and only application level approximation specifications are required, and it is suited to traditional cores, applications, and compilers. And in terms of results, it's able to achieve 20 to 40% mean speed up or energy savings at 90% accuracy, and it's seen to achieve 2 to 15 times higher benefits than prior work thanks to its per operation control. Thank you, and I'm happy to take any questions.
Okay, thank you very much. I cannot turn on my video. So thank you, Gokul, for your presentation. Are there any questions from the panelists or from the audience? And Nico, can you allow videos? Okay. So I don't see Gokul. Gokul, so I do have a question. I said that I would try to get this discussion started. So in the results, right? So it seems, so maybe can you comment on the fact that I can imagine that the bounds that you set, they can be guaranteed, but only for the data that you use for execution. Do you have any benchmarks where the accuracy can be violated, or I mean, the bound of 90% can be violated if you change the data?
Yes. So in fact, yeah, that's exactly correct, that we do not have guarantees. So actually, so the paper discusses for each of these benchmarks, so what is the actual accuracy which is achieved, right? Because even when you use the representative data, okay, so basically the tuning happens for each like epoch of execution, right? So even when you use a characteristic sample for training and say you try to get 90% accuracy, you won't exactly get that 90% accuracy, because even with a characteristic sample, your data is not going to exactly represent it. So, so yes, so the short answer is that we do not provide guarantees, but the idea is that you can set your bounds such that to what extent you're comfortable with some error tolerance, right? So maybe if you have a strict bound for 90% error tolerance, then maybe it's better to set the error bound slightly higher, and so that you provide some buffer for this. But this is, I guess, more suited to like vision applications and all that, wherein you are not like super specific about an exact error tolerance, but you sort of have a rough idea of what estimate you want.
Okay, yeah. So it's important for applications that are kind of approximate, that it can deal with some level of noise, right? Like k-means. I noticed that you had that one.
Right. Exactly.
Okay. maybe also like kind of related, are you aware of works that where you could, because you have these fine-grained annotations of approximation. So I imagine you can model for some operations, you can model how these things propagate, right? So you could extract a data flow graph and then instead of perhaps not, so maybe you don't need to evaluate every time what the result is. Maybe sometimes you can statically predict how errors propagate. Is that something that you had looked into?
Yes. So I'll say not exactly, but one thing we did look into is that so from one tuning epoch to the next tuning epoch, the idea is that there is not much change. If you see there's not much change in the characteristic input samples, which is again often the case if you have like like visual related applications, right? The data you're looking at might not change too much, which means that so the tuning itself does not have to be like it's not that much of an overhead. So because you're not doing a cold start, you're starting from where you started before, right? So but what this would mean is that even if you want to provide better guarantees using some more sophisticated analysis, this doesn't have to be done probably at every fine-grained epoch, but can be done more coarse-grained using like the analysis you're talking about.
Okay, but I'm gonna see if there are some questions that I've missed, the Q&A or the chat. So
yeah,
maybe
yeah, I can talk a little bit more about the slack recycling mechanism because that's sort of integral to the compute approximation.
I actually had a question about the slack, because if I understood correctly, what you're doing is that you're kind of ignoring, like you're ignoring kind of the critical path that you have computed for the hardware operation, right? And so you are it's kind of you're trying to get the results before they actually are ready, right?
Yeah, exactly. So there are two aspects there. So the slack recycling mechanism itself is independent of the approximation work. So that is from our prior work at HPCA 2019. So the idea there is that, so suppose for some operation, you know that the operation is going to take less than one clock cycle. So you know that it's going to take 80% of a clock cycle, for example. And why you know this is that you might have done some characterization that say a critical like 32-bit add operation takes your entire clock cycle, but maybe if you're doing like a 4-bit add or maybe a logical operation, it takes only like half a clock cycle, right? So you know that it is going to take a lesser part of a clock cycle, but then how do you benefit from this? So the slack recycling mechanism itself, what it does is that it optimizes for an out of order core the execution units. So if you have an extra execution unit which is free, so you bring a dependent operation over there and you sort of make the like the bypass path between these operations transparent. Transparent just means that you remove the like the flip flop between them through a transparent path. And so you're allowing data to flow from a producer operation to a consumer operation without clock boundaries. So now in this work, how we are exploiting that
but you're I think we have to cut it short because I think we need to pass to the next
sure.
presentation already. So it was so my question was like, how does it work with carry ripple adder, right? Because you don't know where the error is going to be, and most likely it's going to be in the most significant bits. But I think we'll have to take that offline.
Sure.
Thank you again for your presentation, and we'll move to the next video. So the next presentation is by Adi Rasch. So Adi Rasch his research focus is on compiler technologies, code generation and optimization, as well as programming language design for multi and many core architectures like CPU and GPU. His overall research goal is to achieve performance, portability, and productivity for data parallel computations, with particular focus on formally provable correctness. So he's going to be talking about auto tuning, so kind of related to what we just saw. Please. Excuse me, the audio is not coming through.
Hi everyone, my name is Ari and I'm a PhD student at the University of Münster in Germany. And today I want to present our recent results in the area of automatic performance tuning, or auto tuning in short, especially regarding the tuning of so-called interdependent tuning parameters, all based on our auto tuning framework ATF. Yeah, before we start, so just that you're prepared. So this talk will be actually on a quite high level, which means we will focus on discussing in detail what we are doing and why we are doing the things. And we address the how questions by illustrating our basic ideas only. And details about our approach can be found in the paper. So if this talk can raise your interest, please check them there. So the first thing we should clarify is, so what is for us actually auto-tuning, or how do we look at auto-tuning in this work? And in this work, auto-tuning means automatically identifying the values of so-called performance critical parameters, like for example, the sizes of tiles or numbers of threads. And for this, we assume an already implemented generic code generation approach, which is a generic optimization process based on optimization parameters. And auto-tuning aims at identifying optimized values of these kind of parameters. So an auto-tuning usually consists or works in three major phases. This is the generation, storing, and the exploration of the program-specific search space. And in the first phase, we start from a set of optimization parameters, to which we also refer as tuning parameters in the following. And these are usually identified by their name and the range of possible values. And in the generation phase, starting from this set of optimization parameters, we generate the set of all possible valid parameter configurations, which are in the easiest case all possible combination of parameters values. And in the second step, in the storing phase, we take this parameter configuration and we store them in some kind of data structure. So in the easiest case, this can be a one-dimensional array. And in the last step, this data structure is explored usually by using numerical search techniques like hill climbers or genetic algorithms or the like, or even machine learning based approaches, so that we obtain finally a well-performing configuration. And auto-tuning can be categorized in two major categories. We have special purpose auto-tuning on the one side, and we have general purpose auto-tuning on the other side. And the basic idea in special purpose auto-tuning is that the auto-tuner is specifically designed and tied for the code you actually want to emphasize, we want to auto-tune. And a notable example of such approaches are, for example, the Atlas library for linear algebra routines. I think this is one of the most popular examples. But you have also Puthoor for stencil computations, FFTW for fast Fourier transformations, and so on and so forth. In contrast, the basic idea in general purpose auto-tuning is that the general purpose framework automatically generates a special purpose auto-tuner for the user based on some simple high-level information, like for example, the parameters name and their ranges. And a notable example of general purpose auto-tuning approaches are, for example, OpenTuner. This is from Professor Salman's group at MIT. But we have also kernel tuner and lib tuning and classical approaches like active harmony and Oreo. And we're now briefly comparing the advantages or disadvantages of special purpose auto-tuning versus general purpose auto-tuning. So special purpose auto-tuners usually achieve quite good tuning results, and this because they're specifically designed and optimized towards the application that we want to optimize. However, they have to be designed and implemented from scratch for each new target application, which requires, of course, expert knowledge and is also cumbersome for the user. On the other hand, we have general purpose auto-tuning, and general purpose auto-tuners are actually very convenient to use because they automatically generate a special purpose auto-tuner for us, for the user. However, the current approaches struggle with programs that have these so-called interdependent tuning parameters. And now, what are these interdependent tuning parameters? And here we can see first on the left side, the classic example of independent parameters. So this was the most common example for application that we have seen so far. And independent parameters actually means that each combination of parameters values represent a valid configuration in the search space. Now, when we look at interdependent parameters, their only combination that satisfy a set of constraints represent valid configurations. And if you look, for example, at quite recent architecture, like, for example, GPUs, which have a complex core memory hierarchy, then we usually want to tune tile sizes on different memory layers. And of course, the tile size on the lower layer has to be smaller than or equal to a tile size on an upper layer, because the lower layer tile is only a chunk of the upper layer tile. And these constraints have to be satisfied so that inserted the configuration in the code, in our actual program code, leads to correct program behavior. And now, how are interdependent tuning parameters handled in the current general purpose auto-tuning approaches? So we have on the one side approaches that have no support at all for interdependent parameters. So invalid configuration are just kept in the search space, and this severely hinders the tuners from finding well-performing configurations, as we will show at the end of this talk. And we have on the other side approaches that support these interdependent parameters, but have only limited efficiency because of suboptimal processes to generating, storing, and exploring the search space of these interdependent parameters. And yeah, this is actually exactly where our work aims to start. So we present 3 new contributions of our general purpose auto-tuning framework ATF, which aim to address exactly the weaknesses of special purpose auto-tuning approaches for programs with interdependent tuning parameters. So in particular, we show that ATF generates a search space of interdependent parameters with very high performance. ATF stores such spaces with a low memory footprint, and ATF explores these spaces efficiently. So we aim to contribute to each particular phase of the auto-tuning process for programs with interdependent tuning parameters. And our 3 contributions are mainly based on 2 novel concepts. These are the concepts of parameter constraints and a novel chain of tree structure for representing the spaces of interdependent parameters. So now, just quite briefly, our basic idea to our contributions regarding the particular phases. So regarding the generation phase, so our ATF framework relies on parameter constraints, and the parameter constraints checks constraints on individual parameters, while the traditional search space constraints, which are used by the related approaches, checks full configurations. And this may be a simple design difference, but it's very significant because this design difference enables checking constraints early in the generation process. It enables generating the groups of interdependent parameters independently of each other and also in parallel. And we can also generate individual groups in parallel. Then regarding our storing phase, so ATF search space structure, this chain of tree structure, avoids memory-intensive redundancy that we usually have in the traditional one-dimensional search space representation. So this enables actually implementing important applications in the memory limitations of current state-of-the-art systems. And regarding the exploration phase, our novel chain of tree search space representation allows to be naturally mapped to a multidimensional coordinate space. And the multidimensional coordinate space is actually the most efficient structure for most kinds of search techniques, especially the numerical ones. And thereby we have reduced the complexity of exploring a search space to just exploring a coordinate space. And for these kind of spaces, actually a bunch of existing approaches achieve quite encouraging results already. So now regarding our experimental evaluation, so we have a quite extensive experimental evaluation in our paper, I would say. And here we just present some highlights. And what we want to show is that ATF is able to auto-tune important applications that target both CPU and GPU on real data sets to high performance. And what you can see here is that ATF is able to auto-tune the implementations to even higher performance and hand-optimized approaches. For example, Intel MKN and NVIDIA QBLAS, which are specifically hand-optimized approaches for linear algebra routines on Intel architecture and NVIDIA architecture correspondingly. And we can also achieve better results with our auto-tuned implementation than MKLDNN or NVIDIA QDNN. And especially also, or in particular, compared to other auto-tuning approaches, like for example, CL-Tune, we can sometimes achieve better performance by even orders of magnitude. So if this is interesting for you, please check the details in the paper. So there are a lot of experiments, and these are, as I said, just some highlights. So now just very briefly, one slide so that you have at least one theme, the user interface of ATF. So actually the user interface was the focus of our previous work. And this is just very briefly summarized here on one slide. And if you want to use ATF, what do we have to do? So we take our code that we actually want to auto-tune, and we have to annotate this code by, I would say, easy to use tuning directives. And the directives specify, for example, the tuning parameters by their names and range of possible values, and of course also their constraints. And then ATF automatically generates a special purpose auto-tuner that is specifically optimized and tied to our particular application. Yeah, this is actually the end of my talk. So thanks a lot for listening. And I would be very happy to answer some questions now. And of course, every time via email. Thank you.
So thank you, Ari, for the presentation. Are there any questions from the panelists or from the audience? So there is a question from Felipe Portella. How well ATF performs for unseen workloads? Did you use some leave one group out approach in the evaluations?
I'm not sure if I understand the question right. So actually every workload is usually unseen. Or what do you mean with unseen workloads in particular? Can you elaborate on that a little bit?
I think leave one out. I guess this refers to learning, right? Like it seems like as if you were learning a policy, but I don't think you are learning a policy, right?
Yes, right. So this actually refers to the last part of this auto-tuning step, this exploration step, and there currently we are using numerical search techniques, so we don't expect any kind of workload. So these work quite well for unseen workloads, especially for these kind of workloads. So we don't have to learn a model of these kind of things, and that's exactly the point why we are using these numerical techniques, because they're working out of the box directly.
Okay, thank you. There's a question from Toni Pustinen, rookie question. Are these or some kind of auto-tuning methods used, for example, in the Linux Windows kernel?
I'll be honest, I don't know.
Yeah, I think that's a very different kind of workload, right? It's a different kind of very control-dominated functionality, which where maybe auto-tuning is not heavily used. So we do have a question. So I think it's a very interesting work. I think we could have used that interdependent parameter constraints in our work. So we were using some auto-tuner. So you mentioned that by default, like auto-tuners store all the configurations. To me, that sounds very inefficient, right? Because sometimes all those configurations are really that's a combinatorial explosion. I wonder if you can comment on that. And just as a follow-up to that question, so my understanding is that you generate, like you don't store them explicitly, but you have some generators. Using the constraints, you can generate the combinations of parameters that you want to try out. So I was wondering, like if you don't have an explicit setup of parameters, sometimes you also have kind of symmetries in your design space, like combinations of parameters that you know that would give the same result, or constraints in the step, right? If you're talking about like tiling size, you maybe know that I don't care if it is 10 or 11, but the step is maybe higher. Can you comment on these two things?
Okay, so to the first question, so there we have to differentiate between, as I already said, so there are two kinds of approaches that handle these interdependent, that try to handle the interdependent parameters. The first kind of class is the approaches that ignore these interdependencies. Then actually you don't only have to store the parameters ranges and don't need to generate this entire search space, which makes the memory limitations so quite low. So there you usually don't have any kind of problems by storing the search space. But when you want to generate a space of only valid configurations, where you don't have this in-kind, so where you really consider these constraints, then you have to explicitly generate the search space because you don't have some kind of structure usually. You don't know how the constraints are, and maybe you have some kind of search technique, and these techniques try to iterate over the search space. And maybe they say, okay, give me the first configuration. Then they say, maybe give me the 10th one. And which one do I have to ignore in this space of all in this combinatorial exploded space? And that's why we have to generate this space explicitly. Does this answer your question, the first one?
Yeah, it does.
And then to the second one, so actually with the interdependencies, we're trying to avoid configuration that cause real program errors, crashes. But when you know as an expert, okay, these kind of configurations are maybe valid and my program will work fine with them, but they usually lead to poor performance, and you can also consider them as error configurations and also constrain them out. Usually don't recommend that, because sometimes you have very, very strange parameter configurations that lead to good performance. No one would write these kind of configurations by hand. But if you are very sure and say, for example, maybe on GPUs, many people want to just try powers of 2 for the numbers of threads and these kind of things, and you can constrain all other values out.
Okay, makes sense. There's another question here. Maybe there's time to answer this one quickly. Are heuristic, meta-heuristic algorithms used in your work?
So yes, exactly. We're using exactly these kind of techniques right now. But actually, the work I presented here is not bound to this. So what do we do in the exploration phases? We tell when you have some kind of approach, these kind, how you can tie them to our to our search space. So how is this connection done, and which one you use? Is this a machine learning based, a numerical search technique, or something different? That's up to you. It's just something that has to iterate over the representation that we give to the API that we provide to the technique, and then it can do whatever it wants to find a well-performing configuration.
Yeah. That makes sense. I guess maybe the question is also because, for example, if you use genetic algorithms, then you kind of have to consider the encoding of the genes to match the constraints, I guess. But maybe that's something that can be discussed offline. Thank you, Ari, for your presentation again. So we can move on to the next one. So the third presentation in this session is by Sooraj Puthoor. So he is a member of AMD Research, and he's working on improving GPU performance and programmability. He's also working towards his PhD at UW Madison, sorry, with Professor Mikko Lipasti. His research focuses on increasing the programmability and performance of GPUs in a heterogeneous systems with tightly integrated CPUs and GPUs. He's also one of the lead developers of AMD Gen 5 APU simulator that is used in many recent publications investigating heterogeneous systems. So yeah, looking forward to your talk. Roll the video.
This is Sooraj Puthoor from AMD. I'm going to talk about my paper with Professor Mikko Lipasti, Systems on Chip with Strong Ordering. Executive summary: strong model is intuitive, but performance can suffer. In this paper, we ask the question, can we implement strong model on an APU SoC with low overhead? In this paper, we also introduced lockstep sequential consistency, LSC, for GPUs that accommodates the lockstep execution paradigm of GPU. Finally, we implemented and evaluated LSC and found out that the performance cost was just 0.76% for the GPU phase and 6.11% for the entire application running on the SoC. The outline of the talk is just given here, and I will start with the motivation. Strong models provide intuitive ordering rules, and hence they are easy to program and verify. However, they suffer from performance and area overhead and have complex hardware. On the other hand, weak models allow non-intuitive reordering, and which makes the programming more involved and difficult to verify. But they provide simple hardware with low performance and area overhead. The question is, should we use strong or weak model for programming a system on chip? For example, an accelerated processor unit APU with integrated CPU and GPU. For an APU, for strong model, the hardware gets even more complex with the need for enforcing strict ordering rules across multiple devices. On the other hand, for weak models, the programming gets more difficult with programmers specifying both when to communicate and which all devices that's where to communicate. Here we have a baseline APU system shown on the left with GPUs having multiple compute units or CUs, or streaming multiprocessor in NVIDIA terminology. Each CU has its own private L1 and shared L2 cache. And on the CPU side, we have private L1, private L2 cache, and a shared L3 cache. And they both communicate with the system directory. One prevalent model for APU programming is heterogeneous REST model, which uses synchronization primitives for communication, that is load acquire and store release primitives for communication. In addition to the synchronization primitives, they also define what is called as scopes that defines the work items involved in synchronization. Work item is equivalent to a GPU thread. So the scopes are tied to GPU execution hierarchy. For example, workgroup scope, which says that all the threads within a workgroup or thread block in CUDA terminology should synchronize. Device scope, which says all the threads in a GPU should synchronize. System scope, which says all the threads in the system should synchronize. The implementation of scopes actually naturally evolves to synchronization at the level of memory hierarchy where the participating thread interacts. So consequently, workgroup scope means the synchronization happens at the private L1 in a CU. In a GPU, device scope means the synchronization happens with L2, which is shared between all the threads in a GPU, and then system scope synchronization means the system directory is placed to synchronize. There are some limitations for HRF for discussing that. For highlighting that, we actually zoom in a bit into the GPU, and I have shown a CP or command processor inside the GPU. In this design, which in figure A, the CP, the command processor is hooked up to the shared L2 cache. The command processor is traditionally used for launching work onto GPU, but recent research has shown that it can be used for various other purposes. For example, initiating communication from within a GPU, network communication from within GPU. So the figure A is a design in which the CP is hooked up to the shared L2. On the other hand, figure B, we have a design in which the command processor CP is hooked up to system directory. Now, what should be the scope of communication in that case according to HRF? For figure A, the scope of communication can be device scope, But for figure B or the design B, the scope of communication has to be system scope. This exposes a programmability limitation of the HRF. That is, the HRF exposes the memory hierarchy to the programmer. Also, there is a functional correctness issue when the code written for design A is ported to design B. It will not perform correctly, and that's a portability limitation. A strong model, on the other hand, does not have any of these limitations, and in this paper we ask the question, can we implement a strong model with low overhead? Now I'll introduce lockstep SC, but first question to consider is, what is strong order on GPU? Prior work has told that treat wavefront equal to CPU thread and then enforce sequential consistency ordering rules to the wavefront. However, these prior works did not answer three fundamental questions. First is the program order defined for a wavefront or an individual work item? What should be the ordering between the memory operations from a lockstep executing instruction? And also, what does it mean? What does it mean by extending SC to GPU? Our lockstep SC introduced here answers all these questions, and it assumes a wavefront program order. The reasoning is discussed in the paper, and with wavefront program order, each wavefront there is lockstep executing memory operations, and then the question is, what should be the ordering between the operations that are executing lockstep. So lockstep SC says that can be kept unordered, and with that we have the ordering rules for lockstep. The first rule is basically the memory operations in program order should be in the same order in the memory. That is, program order for the memory operations is same as the memory order for the memory operations. This is directly from sequential consistency. The last is a load sees the last value of store to that address location. That's also sequential consistency. The difference is the equal to P program order or the lockstep executing memory operations. They can be unordered in the memory. So this seems to be a straightforward extension of SC for GPUs, but it's not really that. It's more subtle than that. So, for example, if we take an example in which a thread T0 and T1 of wave 0 is communicating with thread T23 of wave 1, we have a sequential consistency where we have a thread-centric program order, have the valid outcomes listed here in the column. T0, T1s and T2, T6 valid outcomes listed in first row. But with LSC, we have a different valid outcomes for T0 and T1. And then if we have a third model in which we are changing the lockstep executing memory operations unordered rule to appear together in memory, then we have a third model called SLSC, a stricter version of LSC, where we have a third set of valid outcomes. So basically, the takeaway from this is depending on a term as vague as extending SC to GPUs is not accurate. It has to be clearly formally defined, and LSC is our strong model extension of strong model on a GPU, and it's formally defined. So in addition to this, LSC has both programming and hardware design implications, and the details can be found in the paper. Implementation details, we use the fundamental idea of conflict ordering, where the conflicting accesses need to be ordered and the remaining accesses need not be ordered. And we use mutexes for ordering the conflicting accesses. So this mutexes prevents reordering from being visible to other processors. We extend this idea to out-of-order cores in GPU, and our implementation does not interfere with kernel, does not require speculation, and does not require expensive associated hardware. Details can be found in the paper. Finally, to the results, we implemented it using AMD Jump for APU simulator. The simulation parameters are listed here, and they're typical of any GPU papers used in the GPU papers from the past. So here we have the benchmarks which are used on the x-axis. The benchmarks came from Rodinia, XCC, XM Labs, and AMD App SDK. And on the y-axis we have the execution time for the entire application. That's the AP execution time, and you can see that there is a performance degradation, but overall the performance degradation was just 6% across all the validated benchmarks. The natural question is, there is this mutex acquisition latency for implementing the strong order, and why was it just 6%? So the answer lies in this figure, where you can see that the mutex hit rate for all the benchmarks were pretty high. So the mutex acquisition latency did not come in the critical path. For the first two benchmarks, ATM and hash table, which are the outliers, they are fine-grained data sharing benchmarks, and they did not have that much high mutex hit rate. However, the next graph here shows the GPU execution time. That's only the execution time of the GPU phase. where you can see that the GPU execution time of ATM and hash table, the funky data sharing applications, improved because for the HRF model, the software synchronization primitives inserted by the programmer has some overhead. They had to do load acquire and store release operations, which invalidate the cache and so on. But with LSE, there is no such overhead. The hardware takes care of it. And that's why their performance was better with finer grain synchronization. Overall, the GPU performance was less than 1%. Performance penalty was less than 1% for the entire GPU execution phase across all the evaluated benchmarks. To conclude, we introduced LSE, a strong model that accommodates the lockstep execution paradigm of GPU, and demonstrated that LSE can be implemented on an APU with low overhead, and the performance cost was just 0.76% for the GPU and 6.11% for the entire SoC. And finally, I have the AMD disclaimer and attribution, and I will be glad to take any more questions you have. Thank you.
Okay, thank you for that was a lot of information for 10 minutes. We have some questions already in the chat from Ganesh. So the first question is it just that there is a notion of atomicity baked in? Like, for instance, or that is to say, lockstep updates are globally visible in an atomic manner?
Okay, so can you hear me?
Yeah.
Yeah. So there is no notion of atomicity baked in. And we discussed two models, like LSE. In LSE, that's the model we proposed, there is no notion of atomicity baked in across lockstep executing memory operations. But the stricter versions, which I only use for comparison to show that there is another candidate model, that strict version that appear together in memory has atomicity baked in. And that's why we did not implement it, because it's extremely difficult to make the lockstep executing instructions atomically appear in memory. I mean, it may not be atomically happening in memory, but it has to appear to other cores as atom. So LSE does not have it, but that is also another candidate version. That's the gist of the paper. Everyone can think that strong order is one or the other. We have to formally define. Otherwise, these kind of questions will keep on coming up.
Okay, thank you. Yeah, so so you mentioned that this was formally defined. Can you say, like, so when you say formally defined, is this also formally verified in the implementation? Have you used methods of formal verification or like proving that this actually works?
No, I have not used formal verification methods in the paper, but we have analyzed the traces to see that it actually, the implementation uses mutexes. So if the mutex acquisition and releasing is all fine, and then the theory matches with the implementation, that part we have verified with traces, but it's not with a formal verification tool.
Okay, fine. So you also mentioned at the beginning that strong consistency is kind of is cool because it eases programming. So what are the like impact or the consequences for programming models? Is this something that could, so do you see some improvements in the way we program the systems then if this works like this?
Right.
Some simplifications of the programming model? Yeah.
Yeah. So there is a section in the paper where we discuss about implications to the programming model, but we discuss it in 3 steps. It's like there is at the top the application programmer who should not be bothered about it, in our opinion. You should not be, as an application programmer, should not be bothered about the underlying hardware intrinsics. But then there is this middle layer runtime, and then there is this lower runtime layer. So this implication is that the lower runtime layer or the compiler folks, they will have to have this notion that these are the programming rules if the system is othering to the LSE, or if the system is othering to HRF. So that's the place where there is a programming implication. And this makes it easy, we believe, for those low-level programmer writers and compiler writers to think about synchronization, because it has very few rules per se. I mean, you saw 3 ordering rules. They're pretty much sequential consistency with some unordered relaxation for lockstep executing threads. So yeah, there is programming implication, but not directly affecting the application program.
Yeah, that makes sense. Thank you. Thanks for the answer. So I'm going to check the chat or the Q&A. I don't see any other questions. So thank you again, Sooraj, for your presentation. So now we can move on to the fourth presentation of the session. So the fourth presentation is going to be given by Muhammad Huzaifa. He's a PhD student in Computer Science Department at the University of Illinois Urbana-Champaign. He works with Professor Sarita Adve on architectures for extended reality with a focus on designing scalable specialization techniques. He has a bachelor in engineering and in computer engineering from McGill University. So yeah, roll the video.
Hello everyone, my name is Huzaifa, and today I will be talking about our work on inter-kernel reuse-aware thread block scheduling for GPUs. Data movement on chip and off chip is a significant contributor to both execution time and energy in modern GPUs. Although GPUs are now equipped with multi-level cache hierarchies to optimize data movement, these caches are typically poorly utilized. For instance, modern GPU cache coherence protocols flush and invalidate their L1s on kernel boundaries, which makes them unable to exploit data reuse across kernels. However, emerging cache coherence protocols such as Zenovo are able to keep data in the L1 across kernel boundaries while retaining the efficiency of current GPU cache coherence protocols. This presents us with an opportunity to exploit inter-kernel data reuse and optimize data movement. Before we can exploit this reuse, we must first understand the types of dependencies that exist between thread blocks of different kernels. In general, any type of dependency is possible. In practice, however, we found sub-dependencies to be the most common type of dependency in the Rodinia, Parboil, and Pinotia benchmark suites. A sub-dependency is actually quite a simple dependency. It simply means that a thread block will consume the data that it itself produced in the previous kernel. Given this information, we can schedule thread blocks on the same core as before and exploit data reuse at the L1. However, simple thread block schedulers, such as round robin, which is the baseline used by GPGPU Sim, are unable to exploit this reuse. I will now illustrate this with an example. Imagine a system with 4 GPU cores and a kernel with 15 thread blocks. The round-robin scheduler allocates thread blocks to cores one by one, and it keeps doing so until all of the cores are fully saturated. Then, once the cores have executed some thread blocks and space is opened up, they can request more work, and thread blocks are allocated to them on demand. The final schedule may look something like this. Once this kernel finishes, a new one is launched. The previous kernel schedule here is shown in a darker color. The allocation in this kernel will actually be different than the previous one for 2 reasons. One, the allocation will begin from the successor of the core that finished last. This is done in order to ensure uniform usage of the cores throughout the GPU's lifetime. Second, part of the allocation is done on demand, which means there's a certain amount of randomness, and therefore the final schedule may look something like this. Here, it is easy to see that a given thread block in general was executed on 2 different cores in the 2 kernels. Therefore, exploiting inter-kernel reuse at the L1 is not possible for these thread blocks. It is to solve exactly this problem that we proposed several inter-kernel reuse-aware thread block schedulers. The first scheduler, called Chunk, in fact only exploits intra-kernel reuse. The reason behind this is that all of our schedulers employ a technique called chunking, which helps us exploit intra-kernel reuse, and we wanted to separate out the benefits of intra from inter-kernel reuse. This scheduler evenly distributes all of the thread blocks among the cores, such as this. This allocation is kept track of in a simple structure called a chunk entry, which is just a pair of start and end thread block IDs. Once this allocation has been performed, each core executes all of the thread blocks in its chunk entries. Once it is done, it cannot request any more work. In the next kernel, the allocation, similar to round robin, begins from the successor of the core that finished last. In this case, assuming that it was core 2, the final allocation would look something like this. And again, we can see that a given thread block was executed on different cores in the 2 kernels, and therefore inter-kernel reuse is not possible. The next scheduler, called reset, actually attempts to exploit inter-kernel reuse. The initial allocation is exactly the same as chunk, But one difference now is that every time a kernel is launched, allocation always begins from the very first core. So in the next kernel, the allocation will be identical as the previous kernel. And now we can clearly see that a given thread block is executed on the same core as before, and therefore if a self-dependency exists, reuse can be exploited at the L1. The next kernel, called flip, attempts to increase the likelihood of exploiting interkernel reuse at the L1. The allocation scheme is exactly the same as before, but now we introduce the notion of an execution direction. In the first kernel, the direction is from left to right in ascending order, and this is reflected by a direction bit of 0. In the next kernel, the allocation is exactly the same as before, but now the execution direction is flipped and goes in descending order, which is reflected by a direction bit of 1 in the chunk entry. The reason behind this is that in the first kernel, for instance, thread block 7 was the last to execute on core 1. Therefore, its data has the highest likelihood of still being in the L1. So in the next kernel, if we execute thread block 7 first, we maximize our chances of hitting in the L1 cache. All 3 of the proposed schedulers so far statically allocate thread blocks to cores, which may result in load imbalance. To remedy this, the final scheduler, called steal, employs hardware-based work stealing. The initial allocation is exactly the same as before, but now assume that core 3 quickly finishes executing all of its thread blocks and requires more work. Now it will go and attempt to steal a thread block from a remote core. In this case, it will try to steal thread block 3 from core 0. It will insert the ID of the stolen thread block in its steal queue, and then update the chunk entry of core 0 to denote that the stealing has been successfully performed. Other cores may perform similar operations, resulting in a final schedule that looks something like this. Once the kernel is finished, the next kernel is launched, the execution direction is flipped, and now in addition to executing a chunk entry, the core must also execute all of the thread blocks that reside within its steal queue. Our final scheduler only requires a few registers and arithmetic units and 252 bytes of on-chip SRAM, which is less than 0.05% of an entire core's SRAM usage. We evaluated our schedulers in an integrated CPU-GPU simulator. We used 8 regular and 4 irregular applications from Rudinia, Parboil, and Pinotia benchmark suites, and we used 2 different graph inputs for the irregular applications. First, let's take a look at the regular applications. This graph here shows where in the memory system were requests serviced from. Green being the L1, blue the remote L1, yellow the L2, and red being main memory. The different clusters that you see are the different applications. Within each cluster, we have 5 bars, which correspond to the 5 schedulers that we ran. G stands for the GPGPU Sim round robin scheduler, and our 4 schedulers, chunk, reset, flip, and steal, are denoted by C, R, F, and S respectively. As you can see, the general trend is that as we go from the baseline scheduler to the more sophisticated schedulers, the L1 hit rate goes up. On average, we double the L1 hit rate and reduce trips to main memory by 31%. This optimized data movement directly reduces on-chip network traffic by an average of 42% with a maximum of 86% in hotspot. This also reduces execution time by 19% on average and 43% maximum in SRAD v2. The trend in energy is similar, with an average reduction of 11% and a maximum reduction of 21% in stencil. Moving on to the irregular applications, we see a slightly different trend in execution time. Here we can see that the 3 non-stealing schedulers actually degrade performance in certain situations, such as Dijkstra and PageRank, because of the load imbalance that they cause. However, the steal scheduler is able to both achieve load balance and exploit interkernel data reuse at the L1 at the same time, as a result of which it reduces average execution time by 10% with a maximum reduction of 18% in Dijkstra. We see similar results in energy with an average reduction of 8% and a maximum reduction of 19% in Dijkstra. To recap, efficient data movement is critical for continued performance and energy improvements in modern GPUs. To that end, we proposed several inter-kernel reuse-aware thread lock schedulers that are simple, low-cost, decentralized, and do not require any software changes. These schedulers improve performance and energy by 19 and 11% on average for regular applications and 10 and 8% on average for irregular applications. Thank you so much for your time.
Well, thank you, Muhammad, a lot for the very nice presentation. So I'm again checking if there are some questions. I don't see any questions. So I was wondering, like in this case, can you do you have a sense of how far from the optimum you are? I mean, you are of course constrained by simple strategies that you wanted to implement, but do you know what would be the best schedule that would provide the best reuse?
We can't provide Oracle information because things like conflict misses or replacements for other reasons in the caches can cause suboptimal scheduling, for instance. Self-dependencies are also not the only type of dependency. There are other types of dependencies that exist. We are implicitly able to handle them, but not always. All of that being said, in terms of resource usage, we are pretty close to optimal. What I mean by that is that if our steel queue was larger than 32, right, it was 64 or something like that, there would be barely any difference in the amount of performance that we can extract. Okay, yeah, but I guess you could, I mean, at least theoretically, you could construct as the examples that you were showing in the slides, right? So you could abstract actual executions into something that looks like the example, so that you have a model of real application, but of course ignoring all the details. And in that model, you could find what would be the optimum allocation. Great. So in the paper, we actually do have micro benchmarks that you could look at if you're interested, and there are 4 different ones that exercise very specific use cases. So all the data fitting in the L1, for instance, split between L1, L2, and so on and so forth. And those micro benchmarks give us an idea of the types of upper bounds in terms of performance and energy gains that you can achieve. Okay, cool. And maybe since I don't see any other questions, so I think, so I'm not entirely sure, but I think there's been work in task stealing schedulers that are locality aware. So so you have like this combination of some static assignment and then stealing for the rest. Yeah. But what would be if you just implement a stealing strategy that kind of try to give priority to locality, right? So you have a stealing where you maybe don't have randomized stealing, but you have some stealing that is skewed towards reuse. Have you? Right. So we did actually try a few different stealing policies in our scheduler. Something as simple as just steal from your neighboring core, or always start from core 0 or the last one and then move back, and some variation thereof. The results are very application dependent. So based on how memory is laid out and what sort of initial allocation happens, one or the other policy may fare better. But on average, they do appear to be very similar. The other thing is that the reason we actually did this, as you put it, this partly static allocation and partly stealing, is to minimize hardware cost. Because one of the key differences between all the work in work stealing and CPUs is that on CPUs, you typically have a few cores. On GPUs, you have thousands of thread blocks, for instance, many more cores. So keeping track of everything individually can get very expensive. And that's where the chunk entries really do help minimize hardware cost. Okay, makes sense. Okay, checking the chat and the Q&A. No further questions. So thank you very much for your presentation. We can move to the next one. Let me pull the bio. Yeah, so the fifth presentation in this session is from J.Q. Lee. He's a researcher at ARM Research in Austin, Texas. He received a PhD degree in computer science from Georgia Tech in 2013. His research interests lie primarily in improving the performance, power, and security of microarchitectures. So please roll the video.
Can I call you there? Okay.
Hello, everyone. My name is Jaegu Lee from ARM Research. Today, I will present our work, securing branch predictors with two-level encryption. This work has been done with my colleagues, Yasu Ishii and Tam Sonu. As you can see from recent Spectre and Meltdown attacks, side channel attacks expose significant vulnerabilities in modern processors. In particular, side channel attacks exploit branch predictors using branch collisions. To improve the security of branch predictors, in this work, we propose a two-level encryption mechanism. Branch predictor indexing is randomized using simple XOR encryption that enables efficient remapping upon periodic key changes. More robust data encryption improves security further. Our proposed two-level encryption mechanism shows marginal performance degradation with very short epoch lengths with only 654 bytes hardware overhead. Branch predictors are one of the earliest discovered and frequently targeted structures against various side channel attacks. All these attacks utilize branch collisions. Because of the sharing by different contexts within the same physical core, and storing partial tags to reduce storage overhead, accesses from different contexts can fall into the same branch predictor entry. In this way, attackers can maliciously redirect the control flow or inject a malicious target. For example, two code snippets at the bottom show an example of a branch collision. The attacker could intentionally emulate the victim's behavior. Among instructions, these two branch instructions have the same lower bit. If an attacker can control the branch history, these two instructions will access the same branch predictor entry. In this way, branch collisions can enable side channel attacks against branch predictors. In order to mitigate side channel attacks, various techniques have been proposed. One approach is randomizing predictor accesses. By using different index functions per context, an attacker can hardly create branch collisions. For example, if we assume that the attacker and victim have different hash functions for indexing, even with the same branch history and PC, the attacker and victim will access different entries. Any randomization technique requires periodic hash function changes to be more secure. Also, we need to remap entries to different locations using a new index function. Otherwise, we will lose trained information, which leads to performance degradation. Also, an incremental update is preferred not to affect performance by the remapping process. On the other hand, we can encrypt prediction information. For example, the original prediction information on the left will be encrypted using the encryption key shown on the right figure. Similar to randomization, an encryption mechanism also requires periodic key changes and re-encryption for performance. Part of our work resembles the seizure mechanism. Seizure was proposed to mitigate attacks against less level caches. Seizure encrypts physical cache lines with a shared key among all contexts. As explained in the previous slide, Seizure performs gradual remapping to retain existing cache lines to avoid unnecessary cache misses. By obfuscating eviction set formation, Seizure can be effective mitigation with low hardware and performance overhead. However, it cannot be directly applicable to branch predictors due to its limitations. The first limitation is due to using the shared key. Even with the encryption, the same PC and branch history combination will still incur branch collisions. The second limitation comes from the timing requirement difference between the less level cache and branch predictors. Branch predictors are key mechanisms to sustain high front-end bandwidth in a core and lie in the critical timing path. During remapping, a cache line can be remapped to an arbitrary set. This remapping mechanism requires a 1-bit extension to all cache lines to indicate whether the line has been updated with a new key. The extra latency to access this bit to determine which encryption key to use can be trivial for the less level cache, but this is not tolerable in the branch predictors. For more details, please refer to the chained set updates in the paper. To adopt encryption for branch predictors, we need to design an efficient remapping mechanism. As explained, not to degrade performance, the remapping process has to be incrementally performed. As a result, two keys will exist during remapping, and we need to identify which key to use for each access. For example, 3 sets are updated in this example, and the new key needs to be used for these sets. To determine the key, seizure requires a 1-bit extension. For example, the epoch ID field is set for 2nd, 3rd, and 6th set. When the index is 2, the old key leads to set I access, and the new key leads to set J access. By accessing these two EID fields in parallel, we check that the EID bit with the old key is set, which means that this entry has already been remapped. As a result, the new key should be used. Because of EID field accesses, this incurs extra indexing latency, which can violate timing requirement for branch predictors. Instead, we use a swap-based set update mechanism thanks to XOR encryption. We also perform a gradual update from set 0. Set 0 is swapped with set 7 located in the other half. Similarly, set 1 is swapped with set 6. We maintain a pointer to indicate the next set to remap. In this example, the pointer points to set 2. To determine which key to use for indexing, we just need to compare the index and the pointer. For example, when the index is 2, since this is not less than the pointer value, this set is not updated and the old key will be used. This results in deterministic indexing without extra latency. In addition, we swap sets in different banks for quicker remapping by utilizing bank-level parallelism. Although XOR encryption enables efficient remapping, it is not robust enough, and branch collisions can still occur. To overcome XOR encryption's weakness to improve the security of branch predictor further, we implement more robust data encryption. Unlike indexing, we can tolerate up to 2-cycle latency for stronger data encryption. Branch targets stored in BTBs and prediction counters in TAGE predictors are encrypted. One may wonder why data encryption alone is not sufficient. This is because branch collisions still occur without index randomization, and encryption can eventually be reverse engineered. That's why we propose 2-level encryption. For the schematic diagram and pipeline stages, please refer to the paper. Let me move on to evaluations. For performance evaluations, we use a production-level ARM architecture simulator with various spec and Geekbench workload. We use the projected IPC metric. We evaluated various mechanisms. In this presentation, we compare reset that resets all entries upon encryption key changes and beefs up our efficient update mechanism. We made the following observations. Losing prediction information in reset causes significant performance degradation. On the other hand, beefs up shows marginal performance degradation even with very short epochs. The hardware avoid of our mechanism incurs a marginal 654 bytes. Let me conclude the talk. In this work, we propose a 2-level encryption mechanism to mitigate side channel attacks against branch predictors. Index randomization using XOR encryption enables an efficient remapping mechanism upon periodic key changes. More robust data encryption further improves security. We observed marginal performance and hardware avoid even with very short epochs. Thank you very much, and I will take some questions now.
Thank you, JQ, for the presentation. Let me check the chats. So there are no questions. So people today, I guess, is this last session of the day. People are tired, but still, we still have a bunch of attendees. So thank you for your presentation again. Yeah, so this is not my area of expertise, but I was wondering, you have these two levels of encryption, right? And then you justified why you need the second level because of the collisions. So I was wondering, like, how do you evaluate what you gain in security with the added measure? So can you comment on that? I have no idea how that works, right? So how do you, because you said, I mean, you argued that you need this second level of encryption because of the collisions, but is it possible to quantify what you gain and if the cost of adding this second level is needed?
So can you hear me, by the way?
Yeah.
So it's definitely trade-off. So as an industry perspective, security itself is important, but sometimes it's not the top priority. It's usually performance and power. But in my opinion, because of all spectrum meltdown and all side channel attacks, the importance of considering security at the beginning of the processor design, that becomes more important. But how to measure the benefit of security, added security, that's hard to tell, in my opinion. But it has to be fundamentally considered. That's my opinion.
Yeah, that's so I can imagine that that's very difficult, but I guess you could give it to an army of hackers and check how long they need to do something, right?
Yeah, that's how in general the attackers or the hackers, they discover some vulnerability of processors and talk with companies usually and putting an embargo for the public release, and then just that gave companies to some time to prepare some patches or some other mechanism to mitigate those attacks, and then finally those will be kind of disclosed to the public.
Yeah. And I guess in the same line of thought, you show the results for different epochs for how long, I guess, you do changes. So practically speaking, where in those bar plots is this solution going to be used? So is there an intuition of which bar plot is the one that you would suggest people to use?
So it's a longer epoch is definitely better for performance, but that will increase the security kind of breach, possibility of security breach. So I do not suggest like which specific epoch to use in the paper, but my opinion is it's a slightly out of scope from our work, but we have to add some sort of monitoring mechanism to detect whether there is a suspicious activities or not. So meaning, if everything seems to be normal, then we don't have to implement very short epochs because that may affect some performance. So, so my point is, so we have to balance some epoch, but I would say it shouldn't be that short.
Yeah. And is this something that is controlled by some mode or accessible from hardware, or is this just hardware controlled?
It has to be OS and hardware control. So OS will dictate the epoch length, and then hardware can control the epoch length, and then yeah.
Okay, makes sense. So thank you, JQ, again for the talk.
Thank you.
And so we reached the last presentation of today's session and also of the conference, I would say, paper track at least. So the last presentation is going to be given by Ian Briggs. So he's a PhD student at the University of Utah in the States, and he specializes in floating point and system resilience. So roll the video.
Hi, I'm Ian Briggs of the University of Utah, and I'm here to present FP-Detect, which is a tool for protecting stenciled computations. This was the joint work of both the University of Utah as well as the Pacific Northwest National Laboratory. The primary author, Arnab Das, was unavailable to present, and as such, I'll be filling in for him. FP-Detect is a program that protects these stenciled computations by utilizing floating point error analysis to determine if bit flips or compiler bugs have occurred. And these detectors come with guarantees on their coverage and that there will be no false positives. High performance computing needs to be correct. HPC drives many decisions both in the research and enterprise spheres. We need to be able to trust the answers from HPC. Any undetected errors in compilation or execution undermine this trust. Now, as we move forward into exascale computing, it is predicted that soft errors will increase. Soft errors, also known as single event upsets, is when there are bit flips inside a CPU. It can be a single bit flip, it can be multiple bit flips. Now, it doesn't mean that the processor is actually broken. It's just a transient fault, kind of like a hiccup in the execution. This can be caused by marginal transistors or aging transistors, can be caused by heat inside the enclosure, and most famously, it can be caused by high energy particle strikes. So I said we were protecting a stenciled program. This is a simple visualization of a one-dimensional stenciled program. We have space in the X as well as quantized time in the Y. You can see each point is calculated using the values from the previous time step. Now, this pattern of using the previous time steps in a regular fashion makes it amenable to optimizations, specifically polyhedral compilation. Now, this can reorganize the computation to utilize cache locality, or can even automatically parallelize the code. Pluto is one such tool which performs polyhedral compilation via a source-to-source translation of C to C plus OpenMPI. Now, in these type of tools, mistranslations can be hard to catch. So how are we going to solve both soft errors and polyhedral compilation? Well, we could take the code, compile it with two different polyhedral compilers, and run twice. We might be able to do a little bit better than that. If we had a time machine, we could look into the future, figure out what the value should be, then come back in time, let it run out, and see if the two values are the same. But I can't make a time machine. Trust me, I've tried. But what we can do is take advantage of the structure of a stencil computation and unroll it, so that way we can calculate a point many steps into the future, just based on a larger number of points in this original time step. Now, this isn't very computationally efficient and really shouldn't be used to, say, try to jump over everything and compute the final timeline. If it was, then we wouldn't need the time-stepped simulation. So let's try and make this a little bit more efficient before we move on. We can do this via path dominance. So values closer to the center of this region have higher effects on the output than points further along. We can analyze this and determine what the actual influence is of each of these points. And if the influence is small enough, cut off that part of the computation and don't perform it. Well, the computation can speed up a bit, but that still doesn't solve our problem. Well, let's look into what it does guarantee us. So we have the amount of time in the future that the time machine point is going to be calculated for. We have the values that this reduced computation will use. And together, these define this rectangle that has a protected width and a protected height. And what we claim is that in this region, if an error occurs of a high enough magnitude, it will show a difference in the final location. We ensure this via floating point error analysis. We analyze both the time jump computation as well as the time step computation to get to the same point. Now, if you have both these values, then you can determine if their differences can be attributable to just floating point error or something else. If it's beyond the bound of floating point error, then you know something went wrong. Now, the accuracy of this, the amount of the mantissa of a floating point number that we can predict in the future, is a function of both this width and this time steps in the future. You can see if we lowered this point down, we would be much closer to our baseline value, and we could produce a much more accurate prediction. But this rectangle would be proportionately squashed down and protect a smaller area. So I already said that computing the entire line is computationally inefficient and wouldn't work to just detect errors. But if instead of doing just a single point or doing all the points, we did some points along such that these protected areas overlap, then you'd have something like this, where these 3 points protect this region, and these 3 points protect this region. And as such, we can know that our computation did not have any corruption in the entire area. Now, from this, we can estimate overheads due to the number of detectors placed. And this will be proportional to the amount of time steps used and the essential width used, which in turn define the protected width and protected height. Now, that's not a kind of thing that really should be done directly. That's why we split FP detect into 2 phases. In the offline phase, it analyzes the stencil computation as well as user-provided goals for the number of mantissa bits to protect and the overall coverage, and can turn these into this time step value as well as the essential width that can optimize for the lowest overhead with guarantees of the UDP and coverage. These values are then used at runtime to actually implement the detectors. We utilized benchmarks based on these 4 different PDEs: a heat diffusion, the Poisson equation, a second order wave simulation, as well as a convection diffusion simulation. When injecting single event upsets at the software level, we were able to detect both single and multiple bit flips at high rates. The overheads of doing so is rather low in most cases, with an exception for the wave simulation, which required a higher number of detectors and a larger essential width to achieve the same coverage in UDP. Now, coming back to polyhedral compilation, we implemented polyhedral miscompilation, where we injected either a loop bound bug or an array access bug. A loop bound bug is when a for loops bound, either the lower or the upper, is incorrect. An array access bug is where the actual indexing expression is incorrect. When injecting these, we're able to have fairly high detection rates. This is particularly surprising considering for this, we used a low UDP value, which caused almost no overhead in these computations. And thank you. So to bring it all back, we have FP detect, which is a tool that protects stenciled computation and guarantees no false positives, high detection rates, and tunable low overheads. The details of the implementation and evaluations is available in our paper. Thank you.
Yeah, thank you, Ian, for the presentation and also for the time machine comments to loosen up a little bit at the end of the long day. So I wasn't really entirely sure what the role of the polyhedral compiler was at the beginning, because you mentioned at some time that polyhedral compilers are good because they can reorder computation. So I thought you were going to kind of check the reorderings, but then you do the experiments like modifying, like breaking the polyhedral compilers. And in that, when you were talking about polyhedral compilers, I was thinking, how do you define an error if when you reorder computations, the results may change because of floating point accuracies? Is that accounted for in your model of errors, or how does it work?
So the polyhedral compilers should be able to do things like loop reorderings that may be useful and other things like that. But there are certain loop reorderings that will invalidate the computation, right? These loops actually aren't commutable. So what we're looking at is if these types of bugs occur. Now, as far as error introduced by a polyhedral compiler, to my understanding, a polyhedral compiler shouldn't be actually reordering the AST of the computation. So the FP results should be the same, but I could be wrong on that. Sorry, I may have wandered a bit. If you want to restate your question, I'll try better.
No, I think that's fine. I think it's so now we have some comments in the chat, so I think I will consider myself served, and let's check what people are saying here. I think, okay, the first one is not a question, right? Polyhedral compilers are needed for efficient cells in computations also, yeah. The polyhedral compilers can be buggy, yes, there's a piece of work. We detect polyhedral compilers errors as aberrant floating point values. Okay, got it. And so there was this question by Tony Pustinen. Yes, I have seen this concept of polyhedral compilers in this conference a lot. Yes, so there is a special workshop about that in this conference as well, Impact. So the question to you, I guess, Ian, is, are these methods widely used? Could you give some examples where such compilation methods are used and are not used?
To my understanding, they're basically just free performance sitting on the floor. So if your computation can be transformed, it's something that should be. I know LLVM has their own built-in project to allow polyhedral compilations. So sadly, I'm in research, so I don't know practical uses of things, but from my understanding, they're quite useful.
Yeah, so to Tony, yeah, so there's a lot of research. So yeah, the poly is one. Pluto was mentioned before. So yeah, they are restricted to kind of codes, like it's called static affine nested loops or static control paths. So that's kind of the restriction where you can use these things, and that's why stencils, as used in this work, is a common case in which you can use polyhedral compilers. Yeah, okay, so I see that Ganesh is commenting a lot. I just realized that Ganesh is a co-author of this paper, so it's not more than questions. These are comments, and so thank you, Ganesh. Okay, so one thing that I also didn't understand in your talk, I think it was slide 13, where you had this protected square, right? So I think your point was that by detecting an error up here, you can. So if there is no error here, then that square, it was fine. I think that was the point, right?
Yep.
So I was wondering why is the square down here? Because as you said, yeah, so there's a path that kind of leads, so that is more important. I mean, if you do a mistake there, then it's probably going to be reflected up there, right? So in stencil computations, you usually have some constants that multiply old values, like older values. So these constants are usually smaller than 1, right? So one half, third, fourth, depending on the discretization method that you use. So I was wondering why is the box here, and why is not the box going maybe in a triangular fashion all the way to the dot up there? Because so the closer you are to that dot, the more influence you have in the result.
So part of that is just a simplification to make it so the tiling can be visualized more easily. But we're also talking about specific magnitudes of errors. And if a specific magnitude of error were to occur in the area is not highlighted, so either further off to the side or closer to the value, it could have not had enough time to propagate enough to actually cause the visible difference. We do detect things outside of the guaranteed region, and that is mostly dependent on the actual magnitude of the random error. In the paper, we do outline areas which are not included in the proper rectangle of protected values. Yes, the proper shape should be slightly canted off and move a little bit further up. But that's not tileable.
Yeah.
So just have a little bit of overlap.
Okay. Yeah. You also see some comments from Ganesh about this. Okay. So I don't have any further questions. I'm just checking the chat as well. So there's no more input in the chat. So I guess let's thank all the speakers in this session. So you can clap at home. Also, thanks to the audience, the 20 plus that attended this session. I wish you all a very nice end of day, and see you hopefully in one physical event one day or another. Thank you very much.
Hopefully, yes.
Thank you very much. Have fun. Bye-bye.